Okay, we're going to start this one. We're going to look at finding the interval of convergence for three different functions, f prime, and we'll just call this f of x, which is going to be the integral of f. Okay, here f of x is this series. And we have this x minus 5 to the n, all divided by n, 5 to the n. Okay, so the first thing to do is find the radius of convergence. And that will be the same for all three of these functions, the radius. So we'll first find that, and that radius will be the same. Radius of convergence will be the same for all three of these. What might be different will be the interval of convergence, but first let's get the radius. So remember how we find that radius. We find this limit, and we want a sub n plus 1 over a sub n. We want to find this. Okay, so now first of all, notice that the alternating effect will be gone, and we'll just have x minus 5 to the n plus 1, and we'll have an n plus 1, 5 to the n plus 1, like that, times, and all this will be inside. We'll have that n, we'll have 5 to the n, and then x minus 5 to the n, like so. And of course, we want our limit. Let me squeeze that in there. I always forget that. Okay, so this will become the limit. And let's see what we can reduce here. We'll have the x minus 5. Just have one of those. We'll have a 5 left over down here. Okay, and you'll have an n and an n plus 1 here, which we still have. Okay, now this limit isn't too bad. It looks like we're just going to have this x minus 5, that will stay the same, and all of this will just turn into a 5. That limit will be a 5 because it's n over 5n plus 5, which in its limit form becomes just a 5 underneath here. Okay, so that I left out that detail, but n over 5 times n plus 1, that limit becomes just 1/5. So now, if this is going to converge, then this would have to be less than 1. So that means our radius of convergence is a 5. Okay, 5 is the radius. So once you get it into this form, you can see what the radius is. Now, at least for now, the preliminary interval that we're looking at is this. X minus 5 is less than 5, greater than negative 5. So x is less than 10, greater than 0. So this is the interval right now that we're working with. We might be able to add the endpoints 0 or 10 to this interval for one or the other of these. Okay, maybe all three. I doubt it, but you never know. So, so let's check for our first function for f of x. So we're going to check that the endpoints on this one. So what you do is you take this function, and I'll just write it here. And literally you put in 0. You check, what does this series become when x is 0? Well, it becomes this. We have a minus 1 to the n plus 1. And if this is a 0, then this is a minus 5 to the n. And this is an n and a 5 to the n. Okay, so we have to decide if this series converges or not. Little manipulation up here gives you this negative 1 in front of the 5 is raised to the n, so it can be combined with this negative 1 because it's a product. That will be negative 1 to the 2n plus 1. And then you'll have this 5 to the n, and you'll have a 5 to the n here, and you'll have an n. So these cancel. What you notice about this is it looks like, oh, it might be in an alternating series. But when you look at it a little more closely, you realize that when you raise a negative to an odd power, 2n plus 1 is odd power, it stays negative, okay? Negative 1 to the first term would be 3, right? Negative 1 to the third, it's going to be negative 1. Negative 1 to the fifth, and this is 2. It'll still be negative. So really, this is your series. It looks like this. This is just the negative of the harmonic series. This is divergent. Okay, and enough said. We don't have to go through all the testing for that. We're at this point, we know that this is divergent. Okay, so we couldn't add that. Now, what is f of 10? The other side. In other words, we could not add the 0 to the end of this interval. We could not add it. You have to leave it the way it is over there. Now, put the 10 in. We'll have a 1. And so a minus 1 to the n plus 1. And then you'll have 10 minus 5 over here. Makes that a 5. Okay. So 5 to the n over 5 to the n, that's gone. And now we do have a genuine alternating series, right? We have this minus 1 to the n plus 1. And we have over n. That's an alternating series, and you can show by the alternating series test, and you should know how to do that. You can cite it here, but I'm assuming that you can do that on your own. This is convergent by AST. It's actually, it's conditionally convergent, right? We know, because without that negative, it would be 1 over n. And that's harmonic, the harmonic series, which is divergent. So this is, we would call that conditionally convergent. And you'd have to show that the alternating series test does apply to this. We've got a decreasing function, 1 over n, and that is decreasing. It's positive, continuous, decreasing. We've got those conditions for that alternating series test. That was back in, where was that? Was that section 5? Section 5, yeah, that's where we first covered it. Okay, and so this would pass those conditions of the AST, alternating series test. It heads to 0, 1 over n heads to 0, and it's decreasing. You can show that pretty easily. Or you can just say this, this is well enough known to be convergent using the AST. So we were able to add then. So in summary, for f of x, we do have the interval of convergence is 0, 10, like so. So we can write it that way. Okay, now this is going to be, I'm going to stop it here because I'm going to continue this problem in the next recording if you're interested in seeing that. We're going to do the f prime, and we'll do the integral of f also. We still have to test for the endpoints of those two functions to see if that interval can be extended beyond 0 or up to 0, including 10. So we'll call it quits at this point. It's going to get too long. Nobody likes